Welcome back for part 2, where we're going to go through a couple more examples of different sorts of inequalities that don't involve quadratics, but that involve some other kinds of functions. So let's say we have a rational function. So we have a rational, expression. We're not quite a function here. So we have x times x plus 3 over x minus 1 is, we want to know when it's less than 1. Okay, so one thing we can do is we can try looking at cases. So the issue when you have an inequality where you want to multiply both sides by something containing a variable is that you have no way of knowing whether or not the variable is negative. So for any x greater than 1, so if we look right here, we can look at our first case. So case 1, x minus 1 is positive. So if x minus 1 is positive, we know that x is greater than 1. Okay, so for any x greater than 1, when we multiply both sides by x minus 1, the inequality will stay the same. So we have x times x plus 3, and the inequality stays facing in the same direction because we just multiplied by a positive number, is greater than x minus 1. So now we have a quadratic inequality that we have to solve. So we have x squared plus 3x is greater than x minus 1. We can rearrange everything. So we get x squared plus 3x, sorry, not plus 3x, plus 2x plus 1 is less than 0. So we generally, still if we have a quadratic equation, we want to get everything on one side. So now we're looking at a quadratic, so let's find the roots because that'll tell us where it changes from being positive to negative. So here we get x plus 1 squared is less than 0. Now we run into a problem. Here, is there going to be any case where x plus 1 squared is less than 0? No. So on this side, there are not going to be any solutions for x when x is greater than 1. So there's no positive solutions. Okay? As far as we can tell here. So here, next, we're going to look at our case 2. Which is where x is less than 1. So we get x squared, okay, so where x is less than 1. So we get x squared plus 3x. This time we get that it is greater than x minus 1. Okay? So now we are going to go here, we're going to rearrange this. We get x squared plus 2x plus 1 is greater than 0. So here we have x plus 1 squared is greater than 0. So same inequality, different direction of the sign. And at first, it looks like the answer to this is all real numbers. Well, we're squaring this. Of course, it has to be greater than 0. But there is one other case, which is where it is equal to 0. So we get x is all real numbers, but we know that x plus 1 actually can't be equal to 0. Sorry, x plus 1 squared can't be equal to 0, which means x plus 1 can't be equal to 0, which means that x is not allowed to be 1. Negative 1, sorry. So x is not allowed to be negative 1. So here, though, we also have to, so it looks like this is our solution, but we have to remember that for this case, we assumed that x was less than 1. So essentially, we have the solution that x is an element of one of these two intervals. So it can go up to negative 1, it can't be negative 1, and then it can go from there, it can go up to 1. So it has to be between negative infinity and negative 1 union negative 1, comma, positive 1. So it has to be either, it can basically be anything between negative infinity and positive 1, except for negative 1. And if this were a greater than or equal to sign, we would be able to include that negative 1. Okay, so if you don't like cases, and I know that there are plenty of people who don't actually like the thinking involved with figuring out, well, let's assume this and then go through and then come back and check our original assumption. There is a more algebraic way to solve inequalities like these. So what we can do is we can try making the entire rational expression equal to 0. So let's try a different approach, and we're going to rewrite this as x times x plus 3 over x minus 1 minus 1 is less than 0. And now let's use our knowledge of rational expressions to say this is now x times x plus 3 minus, in bracket, x minus 1. And these are both over x minus 1. Okay, and this is less than 0. So when we simplify up here, we still get the same thing, so that we get x plus 1 squared over x minus 1 is less than 0. Okay, so the two places, when we look here, we know that the top part is always going to be positive. So if we have x plus 1 squared over x minus 1, we can look at things that are happening at negative 1 and things that are happening at 1, because those are the two places where our terms may be changing. So x plus 1 squared is going to be positive the whole way through because it's something squared. Okay? And x minus 1 is going to be, when we are less than minus 1, it is going to be negative. When we are between minus 1 and positive 1, it's going to be negative. And once we get bigger than 1, it's going to be positive. So their quotient, x plus 1 squared over x minus 1, here is going to be negative, negative, and positive. So we are given the same ranges. Now we have to think a little bit about the endpoints because we have a less than. We know that 1 is excluded because we would be getting a 0 in the denominator, so that would make our expression on the left not exist, and when it doesn't exist, it can't be less than anything or greater than anything. With negative 1, we look and we say, it has to be strictly less than 0, so that means the numerator is not allowed to be 0 either. Otherwise, it would be equal to 0. So we get the same result from this algebraic exercise, which is that x is an element of negative infinity, negative 1, union, negative 1, 1. So you have to think about whether or not you want to use cases with these rational expression type ones, or whether you want to simply get everything on one side and then make a sign chart and look at the positives or negatives. And if you do that, you have to get it down to one rational expression and then look at where the numerator is positive and where the denominator is positive. And you may want to look at the numerator in pieces. If it's got 3 things that you're multiplying, you may need to look at each of those 3 things that you're multiplying. Okay, if there's 3 factors of the numerator. Okay, last one. I know that everybody really misses Pre-Cal 12, and so we're going to review a couple of lovely bits of Pre-Cal 12. So let's say we wanted to solve, and I'm actually not joking, this really was people's favorite part of Pre-Cal 12. You would think it was, I would have thought it wasn't, but apparently we love polynomial long division. So we've got x to the 4th plus x to the 3rd minus 17x squared less than 21x minus 36. So we want to solve an inequality. So the first thing we have to do, as with any inequalities, is we have to find where we're going to be. Let's get everything on one side, and then we'll find where we're crossing 0. Where are the roots of the expression that we have? And once we find those roots, we will then be able to use those roots to determine which intervals we should be looking for positive and negative, because we can only switch from being positive to being negative at the roots. So let's rearrange everything. we are looking at x to the fourth, let's keep the x to the fourth positive, plus x cubed minus 17 x squared minus 21x plus 36 is less than 0. So we have a quartic. If we were to graph it, f of x, it would be a quartic, a positive quartic, and we're looking at where it's negative. Okay, so in order to do that, we need to solve it. So in order to solve it, we want to use the rational root theorem. So the rational root theorem says that our roots are going to be of the form a over b, where a is the constant term of our polynomial function. We have this works for polynomial functions, and b is the coefficient of the leading term, so the x to the fourth. So basically, we're looking at all the positive and negative factors of 36. So plus and minus 1, 2, 3, 4, 6. And let's start there. Likely we'll have this down. We can continue with listing factors if we like. We have also 9, 12, 20. Am I missing one? No, 24. No, I am missing one. 18. 24 isn't a factor of 36. What are you talking about, Miss Eden? And 36 itself. So now what we're going to do is we're going to just start guessing and checking and plugging some of these in. We're also going to be using, so this is where we are going to use the factor theorem. And the factor theorem says if we can plug in a root, a number, and we get 0, then we have a factor of x minus that number. So let's plug in, let's try p of 1. So let's call this whole thing p. We're going to look at what p of 1 is. So p of 1 is 1 plus 1 minus 17 minus 21 plus 36. 1s are easy to square and cube, which in fact equals 0. How lovely. Got it on the first try. So now we want to find out, I'd rather not be plugging a lot of different roots into a quartic. So I want to figure out if I have a factor of x minus 1, what is left over. So I'm going to do synthetic division, if you recall. So we take the coefficients only of our polynomial, minus 21 plus 36. The first one comes down. The second one we multiply. 1 times 1 is 1. And we put it here, then we add them together. So we get 2. 1 times 2 is 2. We add, we get negative 15. 1 times negative 15 is negative 15. So we get negative 15 up here. And we get negative 36, and then 1 times negative 36 is still negative 36, giving us a lovely 0 remainder. So we now have another polynomial. So we can rewrite this as x minus 1 times x cubed plus 2x squared minus 15x minus 36. Okay, and that is what we're looking at to be less than 0. So now we want to factor it further so that we can find another root of the left-hand side of the inequality. So let's try 2. We can just keep going up through. I might not try negative 1. Let's try 2. So p of 2, and we have to kind of guess and check. So p of 2, usually you can kind of tell when you're looking at it, is 8 plus 8. And now my p, I'm going to use this one because it's a little bit less to do. 8 plus 8 minus 30 minus 36. That one's clearly going to be negative, so not positive. So here we have 8 minus 8 plus 8 plus 30 this time, and minus 36. That's actually close, but not quite. So a little bit more negatives than positives. So now we have p of 3. We get 27 plus 18 plus 45, and taking away 36 is not going to be enough to get rid of that. That's a lot of positive numbers. And now we have p of negative 3, which is negative 27 plus 18 plus 45 minus 36. And that one actually nicely adds up, and we get 0. So now that we know negative 3 is a solution, I'm going to use synthetic division to divide negative 3 into our new polynomial. We're just going to take the coefficients 1, 2, negative 15, and negative 36. We don't want to divide it into the old polynomial because then we'll just get a different cubic. We actually want a quadratic because then we might just be able to factor. Okay, 1 comes down. Negative 3 times 1 is negative 3. Leaves us with negative 1 when we add. Negative 3 times negative 1 is 3. Add that. We get negative 12. Negative 3 times negative 12 is positive 36, leaving us with 0 remainder, as we should get. So that means we have x minus 1, x plus 3, times x squared minus x minus 12 has to be less than 0. So we can factor that final quadratic as x minus 1, x plus 3. This is going to be another x plus 3, and then x minus 4. And this has to be less than 0. So we're going to look at all of our roots. So we have the roots, which is going to be where this, if we think of the left-hand side as a function, so now we would say y equals the left-hand side. We're thinking about on the graph where this would cross the x-axis, so where it would change from being positive to negative. So we are going to draw a lovely little sign chart. So we have our roots. So we have a root at negative 3, we have a root at 1, and we have a root at 4. And so we want to figure out what happens when x is less than minus 3, when x is between minus 3 and positive 1, when x is between 1 and 4, and when x is greater than 4. Notice we're being strict here because our original inequality is strict. It does not include the possibility of being equal to 0. So the roots are not going to be part of our solution. Okay, so now let's look at our different factors. So we have x minus 1. We have x plus 3 squared. I'm going to write it as one term because we always know the squared together is going to come out positive. And this term, we can write the squared because it's going to be changing at the same moment from positive to negative, which it's not going to be changing. We have x minus 4. Okay, so x minus 1 is going to be negative until we hit 1 when it starts being positive. X plus 3 is going to be positive the whole way through. And x minus 4 is going to be negative, negative, still negative here, and then changes to being positive when we hit x is greater than 4. So what we're looking for is we're looking for now our whole expression, so our p of x. When is that going to be positive and negative? Negative, positive, negative gives us a positive when we multiply. 2 negatives, we get a positive. 1, 2 positives, and 1 negative is going to give us a negative, and 3 positives, clearly, if we're multiplying them, gives us a positive. So the only region here where we get a negative result, or less than 0, because that was what our inequality is, you can see we're looking for where it is going to be negative, is going to be where we have a positive times a negative here, and that's going to be in the region between 1 and 4, not including our endpoints. So x has to be between 1 and 4. All right, folks, thanks for taking the time. Sorry this lesson got a little excessively long, and I hope this is the continuation from the last one with function friends and transformations. And I really encourage you to graph. Go ahead, when I've been talking about these things as functions, go graph them on Desmos. Have a look, click on stuff. See where they're actually greater than 0. See where they're not greater than 0. Graph 2 different things and see where they intersect. There's all kinds of fun stuff you can do with this. Right, have a good day. Bye-bye.